Dear participants, we would like to ask you to turn off your microphone, turn on your camera, and use virtual background. The webinar will begin shortly. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to webinar series eTalk 6, Clean Energy and Advanced Materials. Today, August 9, 2023. This webinar is supported by Indonesia Fuel Cell and Hydrogen Energy, IFE, in collaboration with National Research and Innovation Agency, especially Research Group Fuel Cell and Hydrogen Material from Research Center of Advanced Material. We also thank to our sponsor for this webinar series, PT Era Mitra Perdana, PT ITS Science Indonesia, Dynatech, Wiralab Thermovision Scientific, and Technolab Indo Penta Perkasa. Before we start the webinar, let us turn up and singing our national anthem, Indonesia Raya. Thank you. All participants, please be seated. The opening, we would like to invite President of Indonesia Fuel Cell and Hydrogen Energy, IFE, Professor Enia Listiani Dewi, to deliver opening remarks. Please welcome Professor Enia.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Happy good morning for all of the participants for today's webinar series, and also for our partners and sponsors to the this event. We hopefully this will be continue annually, and we will have share knowledge to you about the hydrogen energy and also the advanced material for the topic today. And we are really glad that you come and joined our series meeting. So before we have several discussion and presenting from the speakers, I will share about our progress of the Indonesia Fuel Cell and Hydrogen Energy. Let me share just a few slides for the introduction. Okay, We holding the Indonesia Fuel Cell and Hydrogen Energy Associations. We thanks to the new members that join us, even from university, even from a personal researcher, and also even from industry that now have been joining us. And this is really appreciate. We are really honored to have you all. And for our progress in last June, we have the first Indonesia International Hydrogen Summit that held in the Regis Hotel Jakarta. On behalf of all of the committee, we deliver a special thanks to the sponsors, to the government, to the university, and all of the participants that come from all over the world to join our Indonesia International Hydrogen Summit. Holding this international event during the 2 days, we have many participants, more than 400 participants, and we are successfully to holding this. And we thanks to the ministry that's joining our 2 days event from the 6 ministries, 3 government agencies, 9 universities, and also more than 80 industries. And also from all of the participants, we have more than 9 countries that joining us on that event. This is a really huge discussion that we have in 2 days. And for this event, we are successfully to have a soft launching of National Hydrogen Strategy that's delivered by Mr. Yudo Dwianda Priyadi. He is now become a Director General of Ministry of Energy and Mineral Resources. They committed that hydrogen demand in Indonesia is increasing, and now Ministry of Energy and Mineral Resources join with IFE, with our association, and also several of NGO. We are now making the detail of the roadmap of the hydrogen strategy. But before that, I think you are all will be invited also to joining the engagement of the National Hydrogen Strategy that will launch in the, I think, before the end of this year. And in this concept, in this opening ceremony, we already also deliver the roadmap of hydrogen energy in Indonesia to the Ministry of Energy, to the Energy of Council, and then also to the industry that in here representing by PLN, and also for the international partner of Japan. And we deliver also this all of the roadmap. This detailed roadmap also would be used to make the detailed roadmap of Indonesia. We are happy to share to you. Maybe you can download from our website. This is our suggestion that from make it from BRIN and IFHE, Indonesia Hydrogen Roadmap. In this publication, we will have the landscape of energy in Indonesia, the potential of hydrogen in Indonesia, and also the policy, the policy and regulation in Indonesia right now, which is we have make some revision. We need to make some revision of it. And then also we share about the research and innovation. Also, of course, we in this book, we share about the scenario of how we adopt the hydrogen, including infrastructure, and also the collaboration of international hydrogen supply chain. And the last chapter, we deliver how we can implement it and utilize the hydrogen in Indonesia. Hopefully you can see, you can use our book to make some reference. And then we are happy also to have your opinion, have your critics, or have your additional information. And we will deliver also to the Ministry of Energy and Mineral Resources that make a lead to make a national hydrogen roadmap for the detail until the end of this year. And during the Indonesia International Hydrogen Summit, we are also have a huge declaration for establishing the hydrogen ecosystem among the stakeholders. So you can see that we are really honored and happy that more than 20 industry is joining this declaration. And we are also invite more industry to joining this declaration, because until the end of this year, we will put a detailed action of the hydrogen ecosystem in Indonesia. And we are happy also to having the Indonesia Hydrogen Ambassador that representing by Bu Diah Roro as the Vidya Putri. And then not only the declaration, we are also having the exhibition in our summit. So this declaration, we hope that many participants, not only the industry, but I think the association and also NGO and also the person can join our declaration, because you know, the hydrogen ecosystem we cannot establish in just one stakeholder. We must joining multi-stakeholder, multinational, bilateral, and multi-international engagement. And the basic of this commitment that this government is support all of the ecosystem, and also the parliament also support this ecosystem. Hopefully we will have some action of this ecosystem. This is just a few photograph that you are also to be invited to fulfill this box at here, and we are also have invited all of the industry to join, and we hopefully in the FGD and discussion with the Ministry of Energy, we will have some additional declaration event also in the next month. You will be informed for this. This is, you can see the many stakeholder, ministry, research institutes, and also parliament, the industry of PLN, Pertamina, Toyota, the association also, and Honda, RINA, the Energy Council, and Masyarakat Energy, Renewable Energy in Indonesia, Awina, ARISE, SFC, and Triparta, and also IHI from Japan, and Ministry of Planning, and also Marubeni from Indonesia. So we invite all of you to joining our declaration. And this Indonesia Hydrogen Ambassador will support us also to talk to the many stakeholders in the parliament. And I think Bu Diah Roro will support of our action to make some to establishing the hydrogen in Indonesia. So this is from us, the Indonesia Fuel Cell and Hydrogen Energy. We are really happy to have you all to be members to joining our series and to joining our lecture also in the next future. Thank you so much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Prof. Enia, for your insight in hydrogen activity and also hydrogen ecosystem. Before we continue to our session, I would like to ask for photo group. So please, all participants, you can turn on your camera and then put your best smile. And committee, please help us to take picture. We can start from the first page. I will count down. 3, 2, 1. Okay. And then next page. 3, 2, 1. Okay, we have 4 pages. And then now the third page. 3, 2, 1. Okay, and be prepared for the last page. 3, 2, 1. Okay, we are done with the photo group. Well, I would like to remind all participants that committee has already prepared some door prize for active participant with best question. So please, during the session, you can write your question in chat column, or you can raise your hand during question and answer session. Now, without further ado, please allow me to invite our moderator, Dr. Oka Pradipta Adjasa. He will lead the presentation and discussion session of webinar today. Dr. Oka, time is yours.
Thank you, Mbak Wiku. Ladies and gentlemen, esteemed participants, honored speakers, welcome to our 6th eTalks webinar focusing on clean energy and advanced materials. I'm thrilled to introduce our distinguished speakers for today's session, Dr. Wen Xiong from Micromeritics USA, Dr. Denny Sidki Karidini from the National Research and Innovation Agency, Indonesia. Today, we have the privilege of delving into the realm of clean energy and advanced materials, specifically centered around fuel cell and hydrogen technology. These critical subjects hold the potential to address energy and environmental challenges. For the next few hours, we'll explore recent research progress in the field of fuel cell and hydrogen storage. Throughout the sessions, I encourage all of you to actively engage by submitting your question through the chat or other features. Without further ado, let's embark on this enlightening discussion. For our first session, we would like to extend an invitation to Dr. Wen Xiong. Dr. Xiong, please initiate our conversation or discussion with your insight, analytical method, ensure fuel cell performance, and hydrogen storage material. Dr. Wen Xiong, please.
Thank you. Let me share my screen first. So it's okay to see my screen, right?
Yes. Yes, I
Okay.
can see.
Okay, thank you. Good morning, everyone. I'm Wen Xiong from Micromeritics Instrument Company. I work as an application scientist in Micromeritics. Today, my topic is going to talk about how gas adsorption characterization in the net zero area. First, please allow me to briefly introduce Micromeritics. Our Micromeritics has 3 different production sites. I have been listed here. The one located in Norcross, which is in United States, focus on the adsorption analyzer like the ASAP 2920. I can like people are very familiar with this one, and the free flex. And also we have like ASAP 2460 and the Tristan and so on. And we also have the OutCam, which is our cam absorption analyzer. So the most popular one is OutCam 2 2920. And then we have been updating the 2920 to 2930 here. And then we also have the OuterPool, which is our mercury porosity test analyzer. And we also have some instrument we call AccuPeak or GeoPeak. Those are for the density testing, like the scalar density or the packing density, like that. And then the second size is our at the flow reactor ICCS has been produced in Spain, in Madrid. We are going to talk about a lot of details about FR system and ICCS system later on in my presentation. And we also have universal powder flow tester, which is we call FT4. This one is produced in England. We also have different kinds of application lab in different regions. Those bottom three images are showing our Shanghai demo lab in China. So you are very welcome for visiting or even for like a sample demo testing. The hot topic in 2020, which is now, it is in order to stabilize the climate change, we have to for the CO2 emission to zero, which is we call zero. So the term net zero referring to the target of reducing the greenhouse gas emission to very low limitation, like to involve causing another like global warming to higher temperature. So we have to zero the CO2. We trying to zero the CO2 emission, like by balancing the amount releasing to the atmosphere. So when we say zero, we normally talking about more about the CO2 nature, and absolutely additional. We are also talking about the clean energy without greenhouse emission. So let's look at the carbon nature first. We start from the CO2 capture with the gas adsorbent and the membrane. For example, we do industrial CO2 capture, or sometimes people are also focused on the direct air capture. Then after CO2 capture, we storage those CO2 in a lot of different kinds of function poor materials like MORPHs, people already know, and active carbon like that. Then we storage those CO2, and then if we introducing some catalyst, we can upgrading those CO2 to like fuels or other kinds of chemicals, utilization those CO2 as a feedstock for like producing other hydrocarbons. And also instead of like we mentioned, consuming those traditional fossil energy, which will produce a lot of CO2. Alternative, we can use hydrogen as the most representative clean energy because hydrogen cycle, as we have been seeing in this slides, from the production to the storage all the way to the application, is free of greenhouse emission, especially for some green, like green hydrogen. We are talking about a lot right now, the water electrolysis. So why we are talking about the gas adsorption here, because we are focusing on the net zero. Why we want to talk about the gas adsorption in the net zero area? From the previous two slides, we have been seeing all the process like the CO2 nature or the hydrogen clean energy. All the process about the nitrogen are referring to like the adsorbent, the membranes, and the catalyst, those three different kinds of materials. Most of the adsorbents or the catalyst, as we know, is poor materials. So this comes to our topic. Characterization of the poor materials, like the characterization, the texture or the activity of those materials, is very important topic when we consider doing the, like we mentioned before, the CO2 nature or the hydrogen, all the research in net zero. We have to pay attention to the characterization of those poor materials. And typically, generally, all the research are using the gas adsorption to characterize the poor materials, to check those materials surface area, the pore size or the pore structure of those materials. And we also need to see the porosity of those materials. If we, like we mentioned before, if we are talking about the catalyst, we really want to see the reaction activity of the catalyst. So for those things, That's the things our micromeritics do best. So that's why come to our topic, we are going to talk about the gas adsorption in the net zero era. As everybody knows, the gas adsorption is a very powerful and popular technique for the corrosion of the poor materials, as I mentioned earlier. So adsorption actually is a surface phenomena. So the definition of the gas adsorption is saying the process of those gas molecules attaching to a surface. So they have two different bonding, we can say force or bonding forms. If they are bonding by the van der Waals force, we call it phase adsorption. If they are bonding by the electron sharing or electron transforming, we call it chemabsorption. So the adsorption, the gas adsorption on the surface, actually is basically the process of the accumulation of molecule species at the surface, just on the surface instead of go to the solid or the liquid bulk. Here we are comparing the phase adsorption and the chemabsorption. I guess people are very familiar with it. I'm going to introduce briefly. So when we're talking about the phase adsorption, as I just mentioned, is kind of like bound by the van der Waals force. Is very, very weak bonding. So the adsorption energy is low. It's normally like 20 to 40 kilograms per mole. And also in the chemabsorption process, we kind of have no non-selective adsorption, which means they are local of specific, because the adsorption can adsorb on the surface uniform. We assume it's uniform or everywhere on the surface. So that's why I say no selectivity adsorption. That's because the phase adsorption can occur on the surface everywhere. And also since the weak interaction between the gas molecule to the surface, phase adsorption always happen in low temperature. On the other side, chemabsorption always happen at high temperature. When we say low temperature here, we're normally talking about the liquid argon temperature, which is 77 K. And then at high temperature, we're normally talking about like room temperature or even 50 to 100 degrees C temperature. In some cases, we may need to go a little bit higher, like 150 to 200 degrees C. So that's one of the difference between phase adsorption and chemabsorption. And also, since the bonding by the force is different in chemabsorption, we are trying to check the electron transfer or electron sharing. So the adsorption energy is very high comparing to the phase adsorption. The biggest, like the very universal difference is the selective adsorption happen in chemabsorption. That means the gas molecule has to go to some specific size on the surface for adsorption. Unlike the phase adsorption, you can adsorb on all the surface, but in chemabsorption, you need to find an anchor, which is a specific surface size to attach in the gas molecule. Then let us see how the gas adsorption method working on the adsorbent and the membrane we mentioned before. We usually talk about gas adsorbed physically on the adsorbents. So here we are listed four different kinds of instruments talking about how can we do the gas adsorption, which is the physical gas adsorption characterization on the adsorbent or the membrane. Our 3 flags is ideally suited for the gas, or sometimes we need to do vapor adsorption analyzing for micropores. When we say micropores, we are talking about the pores smaller than 2 nanometer. And we also can do absorption if we are able to check the pore size or the pore structure for micropores. Then we are able to check for mesopores and macropores materials. Then the second one is our BTA, which is breakthrough analyzer. We call it BTA. It is a very flexible gas delivery and the management system if we want to do the precise characterization of the adsorbent performance under process relevant process. When we say process relevant conditions, we are talking about gas flowing system. The BTA can deliver reliable adsorption data for when we want to do gas or even vapor mixture through using a flow-through system. The third one is our macroperimetry analyzer technology. We are using the outer pool to understand when we open different speed and the different accuracy, and also the measurement range. We are able to calculate different kinds of sample parameters, such as we mentioned before, the pore material, the pore size distribution, the total pore volume, and also the pore surface area. The third one is our HPVA. So our HPVA is the same working principle with reflex. We call static volumetric method. But the HPVA is testing the sample under OH high pressure, which we can go up to 100 bar or even 200 bar. So we can, since we are talking about the hydrogen storage, CO2 storage very often right now. So HPVA is a very good tool to do like the hydrogen storage, CO2 storage at a very high temperature, very high pressure, excuse me. So all the physical adsorption measurement in micromagnetics, we are using the static volumetric method, as I just mentioned in the HPVA and the reflex working principle. The static method is actually measuring the adsorption pressure change during the adsorption process. Then we were using the mass balance equation. We were using the gas equation of the state. And then with the measure the pressure, we do the calculation. And then we get the gas adsorption amount. We get the pore size or the pore structure, those parameters. And we also can get like using different models to get the pore volume, pore size, and also the surface area, those numbers. The left figure showing a schematic of the volumetric adsorption setting up is a very easy setting up. Normally it's considering of three different valves, one to the adsorptive, the other one to the vacuum, and then the third one to the sample tube. And we also depends on different kinds of instrument models. We have different range of the produced transducer to measure different kinds of adsorption limitation. So with the pressure transducer, we are able to measure the pressure change during the adsorption. That's kind of like the core center of all the testing. In the physical adsorption process, we start from the start testing the adsorption at very low temperature, at a very low pressure. At its first single molecule or atoms adsorption at some like isolating sites on the surface, and then when we increasing the pressure, we are able to see monolayer surface gas molecule attaching on the surface. And then keep increasing the pressure, we are able to see the gas molecule form multi-layer adsorption on the surface. After we do the measurement, we are going to get the gas adsorption isotherm, which I guess people are very familiar with those ones, the isotherms. The isotherms is plotting with the adsorption volume versus the relative pressure. For the most commercially or the most common instrument measurement, we always measure from the vacuum to atmosphere, which means the relative pressure range from 0 to 1. Our micromoretics has an extensive range of gas adsorption range, often like a convenient solution to realize your research and development, sometimes for quality control, and at some other case for the manufacturing needs. I will show later on our TriStar, our Gemini Reflex ASCP 2416, those phase absorption analyzer associating with application case. Firstly, let's talking about one of the important things for the phase absorption. Okay, so BET surface area. This is one of the model we using to calculate the surface area of the materials after we get the gas adsorption isotherm. Langmuir was the first person who divided using the adsorption study to calculate the surface area of the materials. Langmuir's adsorption was during the adsorption on the surface, only one molar layer of the adsorbent is formed, which means just one molar layer adsorbent, and then the adsorption is triggered by an inactive corrosion. But later on, the BET, those three researchers, they found the Langmuir was assuming one molar layer is not that suitable for most of the case. So they kind of like give their own idea, giving the assumption again. They were talking about 5 different kinds of adsorption. They are saying the most difference from the Langmuir model is the multi-layer adsorption versus the monolayer adsorption. And then they also assume the interaction between the adsorption molecule can be negative. What they consider important is the interaction between the adsorption molecule and the surface. So they kind of like find different kinds of isotherm tape types. As we already know, they have been kind of like clear reported by IUPAC. We have different kinds of isotherms. And then after talking about those assumptions, we have to talk about the application of the BET equation. Most of the customer has been come to us and say, why my BET surface area is like negative or unreasonable. So when you ask those questions, you have to pay attention to the applicationable of the BET equation. In other words, not all the gas adsorption isotherm can use our BET equation to get the BET surface area. That's why your BET surface area in your report doesn't make sense for you. So let's focus on the BET equation. We can see from these two equations, that means how the BET model calculates the surface area. If we want to calculate the surface area, we needed to use the adsorption data to determine the amount of the gas adsorbed on the surface. And then we use the BET equation describes the amount adsorption as showing as a function of pressure here. And then we can transfer this equation to the linear form by knowing the adsorption volume via here at very related relative the pressure from our analyzed data, which is our gas adsorption isotherm. The molecule cavity and capability and the C constant here can calculation from this equation, which is the y-axis or the slope of the fitting data in this linear transmission form. This graph is the corresponding data we call BET transform report. It is important to note that the lenience does not apply to the whole range. For example, here, when the relative pressure lower than 0.05, it doesn't fit in the lenient form. For some like non-porous or mesoporous or macroporous materials, this range is typically between the relative pressure from the 0.5 to the 0.3, which is a very typical PET range. The C constant account for the adsorption answer field for the first layer and the answer field of the condensation. So in this definition, we have to get C constant, which is larger than 0 in our PET report. That means if the C constant is smaller than 0, that means your PET report doesn't make sense. It's like invalid data. The stronger the interaction between the gas molecule with the surface adsorption, we are going to get a higher C value. For the nitrogen at 77 kVars, we normally get 15 to 300 C value, 300 C constant value. Materials with some like especially weak induction, given the lower value, but we normally 15 is one of the band. We normally talk about 20 to 15 is okay. If it's lower than 20, we have to pay attention to how did you get the PET transformation port and then do the calculation. Expect for the PET model. For sure, there are many other models to reduce the gas adsorption isothermal data. So we give some kind of like a general summary here with different kinds of relative pressure range. And then you want to get different kinds of information from your isothermal data. You can apply for different kinds of models to kind of like emphasize your final isothermal report. Our micromeritics have as many as 52 models for applying. So you are very welcome to either visiting our website or looking at our webinar to see which kind of materials is suitable for which kinds of models to get the real like reasonable data as you want. Now let us see some real example to use the PET model to get the PET surface area. Let's get at the studied at with our miscible silica alumina reference materials. The left figure is our TriStar. So here we are using our TriStar 3030, which is TriStar 3030 to do the analyze. Our TriStar give a very I'm sorry you are not able to see the picture underneath. Our TriStar gives a very beautiful isotherm. When we apply the PET equation in the PET range of the whole like the Cambridge isotherm, this is the PET range. Normally we are doing the PET range from the relative pressure from 0.5 to 0.3, which I mentioned earlier. And I also highlight here in gray. And then when we apply the PET equation and the plot it in the linear form, this transfer to the linear form can be done automatically and easily with our instrument software. And then on the right corner is the result showing the PET surface area is about 203 meters square per gram, and with C value equal to 130. So when we're talking about the PET surface area, we have 4 different criteria has been fitting when under the PET equation. We are going to talking about this later. That one of the example I showed before is very typical mesoporous materials. Is very good to apply BET equation to get the BET surface area. Now we are going to talk about the micropores, which are the zero micropores materials. Can we also apply to the BET model for micropores materials? As I mentioned earlier, we have to fit in 4 different kinds of criteria for the BET materials. Theoretically, micropores is kind of like out range of the BET 4 criteria materials. 4 criteria. So we have to figure out how can we use the BET model for the micropores materials. Firstly, when we do the BET data reduction for the micropores zeolite materials here, we get a C value. If you are able to see here, it's a very large negative number. As I explained later, earlier, we are not allowed to rely the data like the report when we get negative C value. So this means the classical BET range, like we mentioned earlier, the relative pressure from 0.05 to 0.3 is not okay. It's not sufficient for the micropores materials. We have to figure out how we can do that. Now we tried to extend the range to a lower relative pressure. And then our software can offer outer BET fitting. This is for Micromeritics software, the BET outfitting script. This script does the automatically BET calculation and check all the 4 criteria of using the BET equation. So in this case, it means when we are using the traditional relative pressure from 0.05 to 0.3, we get a negative C constants. So all this data reduction is incorrect. Then we are jumping to using the BET outfitting script. This is the process how to use the script to do the data reduction. And then we are able to see here, we get a C constant value, which is larger than 0. That makes sense for us. And then we have another 3 different kinds of criteria of using BET equation are also checked here. So that means using our BET outfitting script, we are able to apply the BET equation for the micropores materials. So in this example, the zeolite materials, the data point used for the BET calculation was taken between the 0.03 to 0.03. The relative pressure, which is very different from the regular BET relative pressure. Here I'm going to talk another example of for some very low surface area materials like wood. Our TriStar was given a very weird. This is the green isotherm here. So the isotherm goes down, which means nothing for us. So it's getting a very weird isotherm. The decreasing amount of the quantity adsorbed with the increasing pressure. That doesn't make sense. There are many different reasons that can lead to like the negative trend. For example, the leaking and the insufficient degassing of the sample. A change of the analyzed temperature during the isotherm also can lead to some like change or some testing error for the free space, or the measurement can also decreasing the quantity adsorbed with the relative pressure. But another reason could be the efficiency equivalent. That means we don't have enough pressure equivalent using TriStar, and then we can switch to our another product, which is Gemini here. When we use the Gemini to analyze the low surface area materials, we get a better isotherm, which is the red line here. resulting with accurate BET surface area, which you can see from here, the red line. The BET surface area is about 0.98 meter square per gram. So in this plastic, we are saying with the low surface area materials, our Gemini can be a preferred way of running and offering unique advantage over the Tri-Star. Now let's see some real example to check in how the pore materials or the pore size or the pore structure affect the adsorbent or the membrane performance. Process distribution is the key parameters for the MOFs used for the, especially for the gas adsorption, gas separation application in this case. So the customer were using our ASAP 2460, collected a good isotherm of the materials. The data reduction showing the pore size calculated, they were using HK model is about 8 to 11 angstrom. So if we look at the different kinds of gas molecule diameter, we are able to see the 8 to 11 angstrom pores size can be accessible to CO2 molecules with the 3.3 or 3.4 angstrom in diameter, but not able to let the PEGS with the diameter in 21 or 20 go through. So use those materials is able to separate CO2 from the PEGS. As I mentioned earlier, our 3FLAX has a superior micropores performance for high-end research in emerging materials for adsorption. For the customer materials, the FISIC-3-NIC, the nitrogen is unable to diffuse into those narrow pores in the materials. So they were instantly using the CO2 for the testing. CO2 can very easily go to the pore channel even at high temperature comparing to the liquid argon temperature. So here I'm happy to show an example of using our 3FLAX to check the micropores, especially micropores, very narrow small pores, structure adsorption mechanism. Here is an example of using 3FLAX to determine very tiny difference, just to do a little bit of the surface multiplication of the lithium iron phosphate materials. So we were doing the surface multiplication by ALD, which is the atoms layer deposition on the surface. So from the isotherm, we are going to see the specific surface area of the lithium iron phosphate only changes slightly from 5.17 to 5.36, but we focus on the C value change here. The C value changed dramatically from the 94.7 to 50.5. That means using our 3FLAX, the very high performance instrument, we are able to use in the nitrogen molecule to determine the tiny, which is very small surface multiplication on the surface. Here is an example we talked about earlier about the breakthrough analyzer. So all the example we talked about so far is talking about single component gas adsorption on the adsorbent or the membrane. That means we can use the static method to test those single component gas adsorption. If we come to like multiple component adsorption on the surface, well, there is a term we call competitive adsorption. So for example, if we have CO2, water, nitrogen, hydrogen, different kinds of gas mixed together goes into adsorbent, then the adsorbent has a different kinds of selective or adsorption capability of different gas. So those mixture of gas can happen some competitive adsorption on the and on the adsorbent. So when we needed to check the adsorptive behavior under real industry conditions like a mixed gas mixture, we have to thinking of use the breakthrough analyzer to do the dynamic column breakthrough analysis. So the left figure shows in the presence of CO2, the water uptake decrease. So we see the competitive water, and then that's the competitive CO2. For this competitive analysis, we have to use the BET to do the analysis. If you are interested in doing the breakthrough analysis, you are very welcome to visit our website or looking at our webinar or directly contact to us. And the last example I want to show talking about the adsorption and the membrane solution is the high pressure adsorption. So the HPV2 I mentioned earlier, here is an example of the hydrogen storage using HPVA to check in the storage capability at high pressure. So we look at 3 different kinds of materials, and then in 2 different kinds of temperatures, we check the hydrogen storage capability at 35 bars. So that's the results showing on the right. And then the middle figure is the isotherm of the adsorption, quantity adsorbed versus the pressure, which is a high pressure in this case. So now we are I'm done with talking about the adsorbent and membrane solution. In the second part, I want to talk about some details about the catalyst solution. As I mentioned before, we normally use the Fitzoption, like the Fitzoption, physical gas adsorption, to check the texture property of the catalyst support. This is the first stage characterization of the catalyst. And then at the second stage of the catalyst is trying to characterization the catalyst itself, like the supporting the metal catalyst, some metal oxide surface, some zeolites, some MOFs, those kind of catalyst, using the catalyst chemabsorption characterization to do the catalyst activity or selectivity evaluation. I also list 4 different kinds of instrument here. We are going to talk about the ICC and FR later on in details, so we are going to skip this one. AutoChem, I'm going to talk about this in detail since this is our new updating AutoChem. The 3-flex chemabsorption. So if we can recall, I was talking about 3-flex also in our adsorbent or membrane solution. So when we're talking about the Fitzoption, our 3-flex, like I mentioned, can do like a very good instrument for micropores all the way to the macropores. So if we are also want to use the same instrument 3-flex to do some like chemabsorption, which is the, as we all know, the post chemabsorption, temperature program reduction, temperature program oxidation, different kinds of temperature program analysis, we can upgrade in our 3-flex to do the chemabsorption analysis. Okay. Let's look at our AutoChem 32930 first. The AutoChem, the series of AutoChem, we used to have AutoChem 22920 is the most widely used and highly cited system for the catalyst reactive characterization because the 2920 is the most automatically, like very high level, automatically high accuracy system for chemabsorption and for the temperature program reactions. In 2020, we have been upgrading our 2920 to our 2930, which is the AutoCAM 3 here. We are see. The new AutoCAM can meet and execute the performance with a design that save you like hours per day, like for example, 30 minutes per each, like 30 minutes each experiments, and can make the most sensitive, reproducible measurement. And also we have been upgrading the operator safety. Let's see some of the very interesting upgrading point here. First one is our AutoCool on this corner. The new AutoCool is an integrated gas feeding system, which can rapidly cool the sample tube, like from the high temperature to room temperature. When we are before loading a new sample or doing the experiment, for example, sometimes we have to pre-treat the sample to some high temperature and then cooling down to do the analysis. So the AutoCool is typically can save 30 minutes fasting than the old, which is the 2930, and the AutoCool requires no liquid and external support. Is just by voltage for us to do the cooling. Another upgrading is our TCD. So the TCD has been upgrading. The design is totally different. For our new AutoCAM, it can have like more than 2 times sensitive, which is 110% more sensitive than our previous design. This can enable the customer to use lower sample mass. This is very useful. Lower sample mass to do the testing. The third one I want to talk about is our Quick Connect sample loading. I'm going to show you a picture and a very short video to show to see how the Quick Connect working. We call it the loading a sample is a snap. How the snap working? We are going to see it later. There's another very useful upgrading is about the gas inlet here. So on our 2920, we have 4 gas inlets for 3 different kinds of ports. So totally 12. Now we have been upgrading 4 gas inlets to 6 for each port, and totally 18 gas inlets. Allow you to have the gas concentration or gas consumption when you need it. So you do not need to introduce any error or any extra work by switching the gas line from the current one to the one you really want. So now let's go to see the Quick Connect, which I mentioned. I really like this design. So this is our patented new Quick Connect sample loading. So the new design has been putting these 2 different like separate species together, and then we were not using the nut for sealing. We were using the snapping for the sealing. With this design, we are able to make the sample tube installation very fast. Which we say maybe 1-2 seconds, very easy and more reliable than our traditional design. Because as I mentioned, we are using 2 different separate pieces instead of going to one species. We also, by using this design, we can reduce the risk of breaking the sample tube. As you can see from the picture, and also you're going to see in later video, we just need 1 hand to hold the sample tube. In the previous design, we have to use 2 hands to hold the sample tube, which is very, very, or we can say it has high risk to break the sample tube. Now let's see how the snap look working. Okay, So as you can see from previously, we just need one hand to holding the sample tube, as you can see here. And then with the click, we kind of we call snapping the sample. All the loading process is easy and faster. And here is our new vapor source generation mantle. It's much more easier. It's much easier to operate, as you can see from the video. So if you want to see more details about our AutoCAM 3, like I just mentioned earlier, you are welcome to connect us to see all the details. We can explain more details to you, and we also can send you some like documents or video to see how this how the new AutoCAM upgrading. Okay. After briefly introducing our 2930, now let's go to see some real application case. First, let's start from our catalyst support. As I mentioned earlier, we were using the feed absorption analyze to check the catalyst support. We normally see the support surface area. So the left figure is showing one example of measuring the BD surface area before synthesis of the support. The reason for that is the author was using a strong electrostatic adsorption synthesis method. So they have to know the surface area of the support to calculate the surface loading and calculate the final platinum wedge loading on the support. The figure on the right showing the texture difference. We can see two different isotherm before the precursor impregnation and after the precursor impregnation. This is by using our phase absorption gas adsorption isotherm to check the difference of the catalyst support. The second example is using the hydrogen post-chem absorption. Actually, it's oxygen precursor hydrogen post-chem absorption by our AutoCAM 2920 on the platinum carbon-supported platinum catalyst. This is a very good example of using chem absorption in the PEM fuel cell catalyst. So if we look at the right figure, we can see 5 different kinds of selective analysis was conducted for this sample, as well as the other platinum, some other platinum carbon supported platinum sample to determine the reproducible or for using chem absorption to characterization the catalyst. The determination of the platinum surface area concentration and the platinum surface area getting from the chem absorption contain no assumption. That's the very, very big advantage of chem absorption. It does no adsorption when we're calculating the platinum surface size. The other advantage is larger enough sample size. When we say larger enough, we are comparing the CV test. The CV test sample mass. So as I mentioned in the previous slide, the PEM fuel cell application here, we have to check the platinum surface size by the CV test to see the real electrochemical platinum surface size. So the author was using 4 different kinds of characterization to comparing the platinum surface size. Each method of analysis was repeated. They were doing enough number for the repeating to determine the reproducible and the standard deviation limitation. So the comparing results showing the platinum surface site concentration is very high, is much high for chemabsorption comparing to the XRD and TEM. That's because our TEM or XRD, so XRD has very has higher results than others because they were using the assumption from the share equation. And as we all know, for the TEM data, we have to collect a lot of particle numbers. It's a lot of work to do the calculation, get the platinum surface size. So that makes sense. Chemabsorption is like a good alternative, easy one, simple one, quicker one to get the platinum surface size. And also, like I said, without any assumption. And also people will say, okay, CV test should be due. Sure, I agree with that. But for the CV test, we were using very tiny sample. So for example, we are using 0.01 gram sample for the testing. It's not very representative for the sample. So here I give the suggestion using both chemabsorption and CV to do the test, get a very kind of like eliminating the test limitation for each method and get a very good result to considering the concentration of surface platinum sites. Okay, the second example of the catalyst characterization is the hydrogen temperature probe reduction. So TPR is most widely used characterization to determine the quantity of the reduced species. Understanding the stress of the interaction between the metal and the support. So the left figure here is an example of the hydrogen temperature program reduction curve. In the curve is showing 3 different kinds of peaks. So the first peaks at the temperature range from 320 to 380 is showing the cobalt oxide reduced to cobalt at relative low pressure. And also we can see the peak at the 450 degrees C is digested to the nickel oxide reduction to nickel. So in this case, it means the different kinds of metal has different kinds of interaction with the support. So the surface, when we were doing the TPR to check the stress of the interaction, we really want to see the relationship between the surface reducible of the support between the activity size or the selectivity of the sample. Here is an example of the oxygen temperature program reduction, also using our AutoChem as a powerful tool to study the oxygen species. The oxygen species adsorption on the surface. So from the left figure, we are able to see the oxygen desorption peak temperature has been divided into 3 different kinds of temperature range. For the lower temperature range, we kind of like see the oxygen adsorption on the surface, like how much is it? How about like how many oxygen has been adsorbed on the surface? For the peak at the moderate temperature, which is high temperature 450 degrees C, we can see those oxygen has been adsorbed on the oxygen vacancy. So by calculating the oxygen amount, we are able to see how much vacancy in the sample. The third high temperature, like oxygen desorption temperature here, means the oxygen has been go through into the sample lattice, and then it take like more energy, which means high temperature to get those oxygen out from the sample. Here is the temperature program oxygen. So temperature program oxygen can help to determine the deacidification reason of the carbon deposition after reaction. I'm giving an example of the nickel. From the temperature program oxygen curve, we can see the oxygen consumption. So this is oxygen consumption curve at 300 degrees C and 600 degrees C. If we are looking at the right figure is the CO2 production curve. If we look at the 300 degrees C, there's information here. So at 300 degrees C, we can see oxygen consumed and we can see CO2 produced. This means the carbon deposition on nickel has been happened and can burn off the carbon species at 300 degrees C. Okay, we do the same thing at 600 degrees C, since we see the oxygen consumption at 600 degrees C. At 600 degrees C, we are not able to see any CO2 product produced. So this means the oxygen consumed on at 600 degrees C oxidized the nickel catalyst. So that's why we are not able to see CO2 production. So I have been talking about the post-chem absorption, temperature program reduction, temperature program desorption, and the temperature program oxygen to characterization catalyst. So if you are interested about those characterization methods, you can check my slides. Also, you also can find the relative reference to see the procedure, how to do that. Finally, I would like to introduce the in-situ gas adsorption characterization for catalyst. This is a new promoting method by Micromeritics in-situ gas adsorption. So now here I'm using the methanol, the methane dry reforming reaction on the nickel catalyst as an example. So as we always know, the methane dry reforming is always operated at a very high temperature, like 500 degrees C to 650 degrees C. So at this high temperature, we cause the nickel deacidification either by the carbon deposition or sintering. If we want to check the deacidification of the nickel catalyst, we are able to see all the the results or the reason we mentioned here in one experiment by using in-situ gas adsorption system. The in-situ gas adsorption system will help us easier, quicker to check the deacidification mechanism. So how the in-situ gas adsorption work? Let's look at the two instruments. If we combine our Micromeritics ICCS, this is one of the instruments, FR system, that's the other system. If we combine these two systems together, we are able to do the in-situ gas adsorption. In-situ study the change of the nickel catalyst during the methane dry reforming process. Now let us see how this procedure works. The experimental procedure is very, very simple. So the left figure is the schematic of combine the ICCS, which is the red dash line here, combined with the Ultra ICC FR system to do the experiments. First, we load the nickel catalyst into the FR sample tube, as shown here. Then we either flow CO or hydrogen, different kinds of gases you need, from the ICC system all the way to the sample tube to conduct the post-chem absorption on nickel catalyst, calculations the dispersion before the reaction. And then thirdly, we flow the CO2 and the methane to the catalyst. To recording the production from the sample tube as a function of time, or as a function of temperature, or as a function of pressure, whatever you want to check the dry reforming performance of the nickel catalyst. We can go to the separator to separate the production, like for example, the water or methane from the reaction, or other products, whatever you want. And then we do the online recording by either MS or the GC to record the reaction product. And then after we do the reaction as we want, get enough kinetic data we want, we switch, we kind of like close the CO2 and the CH4 from the FR system, then switch back to the ICCS system. We introduce the oxygen from the ICCS, go through the sample to do the temperature program oxidation, to check the carbon deposition on the surface. We also can do the same thing, like introducing the CO or hydrogen from the ICCS, do the post-chem absorption on the nickel catalyst, and then also check the nickel catalyst dispersion after reaction. So in the whole process, like the whole experiments, the nickel catalyst is inside of the sample tube, never taken out, never taken out. That's why we say ensuite gas adsorption on the catalyst. Now let's look at what kind of data can we get from one experiment. We just load in the sample and then get all the data we have. This interesting chemabsorption prototype code here has been proposed by the author. If you are interested about the chemabsorption prototype, you are welcome to look at the reference. I'm going to just explain using the hydrogen dissolved amount here to represent the platinum surface size. Again, we are the author was using hydrogen dissolved amount from the surface to represent the platinum surface size. So they check the hydrogen dissolved amount every 4H, like 12 hours, every like a reaction time change to see the nickel surface size change, as we can see from here. And then when we look at the right figure, the summarize the results showing the nickel dispersion changes. So if we look at the commercial one, we are able to see after 40 hours experiments, then nickel lost all the surface size. That means the nickel either been sintering, so they lost all the surface size, sintering to a very big particles, or has some carbon deposited on the nickel surface. So the customer also did a temperature program reduction, temperature program oxidation on the like the deactivated nickel surface. So when they are doing the temperature oxygen characterization, they are able to recover the nickel surface here, which all the way go to the same number as the time equals 0. So the conclusion here is customers see the carbon deposition on nickel surface, and also see the carbon, also see the nickel sintering during the reaction based on the dispersion changes in the dry reforming reaction. So this is I'm giving an example of using ensuite gas adsorption to characterization the nickel catalyst and to study the deactivation mechanism in one experiment. I emphasize one experiment. Just loading the sample to the catalyst and then doing all the ensuite gas adsorption. This is all I have today. Really thank you for your attention and thank you for your time. I guess my question slot will be later, right?
Yes. Yes, we will have a question and answer after Dr. Danny. talk.
Okay. Okay. So I will come back later for the questions.
Yeah, thank you. Thank you, Dr. Wen Xiao, for interesting talk. And for the next session, I would like to extend an invitation to my colleague, Dr. Denny Shitki Khairuddini. He is a research professor from Green. Dr. Denny, please enlighten us with your insight on the research prospect of carbonaceous-based hydrogen storage material, please.
Thank you, Dr. Alvin. Please let me share my PPT first. Hello? Okay. I hope my audio and video no any problem. Okay. Good morning, everyone, to my fellow research scientists, to my fellow engineer, industries, and also all participants. Thank you for joining our webinar. This is our 6th webinar, and in this occasion, I would like to share with the topic about this prospect of carbonaceous-based hydrogen storage material. And I'm Denny. I'm a research scientist in BRIN. Okay, this is just a little bit about me. Maybe I just highlight it. And then, okay. Before Dr. Xiong already mentioned about many technical aspects on how to measure the quality of the gas absorption or dissolvation and etc. Later, I will showing to you about some of application, but focusing only for the carbon-based material, carbon-based adsorbent materials. Okay, before I going further, I would like to highlight again. In here, I would my focusing of talking about the hydrogen. So I just want to sharing again what the hydrogen is. Actually, if you can see there from the screen, there are so many colors, right? The rainbow of hydrogen, and this is the meaning from the source and the process actually. All the hydrogen is same H2, but the process it will make some different of the carbon footprint, and therefore, and of course, that also will affect into the cost of the price of the hydrogen per kg itself for sure, because we talking about we concern all of the world already agree about the net zero emission. Therefore, we are going to the green hydrogen, the lowest part, this one. But of course, currently the price is still high comparing with the fossil base. However, there are many research institutes in the world trying to make it the lower cost of the hydrogen production in the real application. Okay. So this is just to remind you what about the physical properties of the hydrogen molecular. This is the mass molecular of the hydrogen, about 2 point something gram per mole, and the melting point, this is about minus 259, and this is the boiling point, minus 253 degrees C, and the critical temperature about minus 239 or minus 240 maybe, in the about 13 bar. So this is showing that the hydrogen is rather difficult to control, to storage, even or to transport itself. If you want to make it in the liquid condition, it will be in very low temperature, in the cryogenic or the low critical temperature. And as you can see from here, the density is very low, about 0.08 kg per meter cubic, meaning the volumetric is very low, the gravimetric may be high, but the volumetric is very low. As you can see here, the density in the liquid state, I'm sorry, this is to be minus 253. It's about 70 kg per meter cubic. And HSP and LHP, the number, for sure, this superior comparing with other fuel, fossil fuel. And yeah, if we talk about the storage of the hydrogen, there are many requirements, the technical or the some technical requirement that we have to overcome. This number I already mentioned before, the LHP and the HSP of the hydrogen. However, at the ambient condition or at 100 Kelvin, about 27 degrees Celsius and 1 atm ATM condition. So the energy content of 1 liter meaning it's very huge volume. 1 liter of hydrogen is only 10.7 kilojoule. So the order of magnitude too low for practical application for sure. It is not ideal for practical applications. And there are some issues that we need to overcome about these 3-point issues. So what are the options available for storage? Maybe Dr. Xiong already highlighted a little about the storage of the gas. And she also already mentioned about the hydrogen storage and the performance testing of the storage distribution of the material for the hydrogen storage. So what are the theoretical limits to storage density and how close can we come? And how do we organize a development program to achieve adequate store energy in efficient, safe, and cost-effective manner? So we should have many homework in here. And this is the challenges for us, for the engineer, for the researcher, all of the world, in order to make the hydrogen happen in reality. Okay. This is just to remind you again, the comparison of the hydrogen storage method regarding the hydrogen. So we are focusing on the hydrogen when it stored, or what kind of the method like compressed gas. This is the physical one, the liquid state. So this is in the cryogenic condition, minus 253 degrees Celsius. Physics option, this is maybe we will talk about more. So this is about the absorption, physical absorption by porous material. So there are many porous material actually, but in here I will focusing more on the carbon. And for sure, Dr. Xiong also already mentioned that for the physical absorption, it can reversible, a little bit different with the chemical one. And then this is metal hydride. The metal hydride, I will highlight it maybe a little bit. So there are some advantage, disadvantage all of this method. And then the compact hydride and chemical hydride also. There are actually many. And in this next slide, I will showing you the more many option, the other main option of the storage of the hydrogen. So what kind of the important characteristic for the hydrogen stored media or the sorbent material? There are, if I concluded, there are 7 points in here, like the high hydrogen content per unit mass and unit volume. So this is that we need to concern. And the number 2, low energy loss during operation. So we need also to pay attention on this, because the hydrogen is very small molecule. Fast charging and discharging kinetic. This is regarding when we store and when we want to release or we want to use it. And then the highly stable with long lifetime operational cycle. For sure, every equipment, every technology, we want to have the long life operational cycle. And then the safety during normal operation or accident, we need to diminish, we need to decrease as low as possible. Limited hydrogen loss during inactivity. Yes, because the hydrogen is very small molecule and it can passively evaporate or maybe react with the other element from the storage tank or whatever. And the cost of manufacturing and supportive infrastructure indeed, yes. So this is the 7 characteristic that we need to consider when we want to develop the storage media of the hydrogen. Okay, I just want to highlight again. So from the right side of model, you can see that the compress and the liquefy the hydrogen, where those technique is the physical method, physical way for the store the hydrogen, and this is relatively established. Right? the liquefy or the liquid hydrogen is in the cryogenic state in the minus 353 degrees Celsius. Meanwhile, the compressed one, currently we have two options, 250 and 700 bar. So from the left side of this figure, you can see the gravimetric density of the hydrogen is very high, but the volumetric of the density is very low comparing with the other fuel, for instance, like ethanol, propane, diesel, gasoline, or any other fuel. If we want to increase the volumetric, it should be compressed. So when it compressed using 350 bar, it increased a little, but the volumetric density 700 higher a little, and the liquid more higher. But when compared with methane, methanol, the volumetric is still lower. But again, in terms of the gravimetric, the hydrogen is the superior. Okay, so this is just the illustration of the many or the various state of the storage of the hydrogen in the liquid. In the top figure, left side is the liquid state, and then in the center, the compressed state, and the right side is the cryo-compressed. So the cryo-compressed is the combination compressed with the liquid with the cryogenic condition. So the volumetric density will increase more comparing with those two previous technique. But we are in the research in all of the world. Also, many scientists also try to develop other method to storage or to transport the hydrogen. So in here we will talk about more on the physically adsorbed hydrogen on the bottom left, the bottom left. So this is the one that highlighted previously also by Dr. Siong. There are some the physical adsorbent of the interaction of the gas, including the hydrogen for sure, with the material. So what kind of the material that's suitable that we want to discuss more in this session. There are also metallic hydride. This is a more established. Black hydride also the similar one, and LOHC, the liquid organic hydrogen carrier. For instance, using toluene, it become the MCH metal cyclohexane. This one also already starting in the pilot plant. The one that I know is in the Brunei to Yokohama by some Shell and some Japan company. There has some cooperation on it. Okay, going further. Okay, so regarding the main technique that I already mentioned, so if we want to compare the reason why we need to go to the carbon absorption or the fish desorption process, as you can see here, yeah, the compressed one is the simplest one. However, the density of storage is still low compared with other method. Yeah, in order for the possibility, the compress is the easiest way because it's already established in many industry also already apply the compressing whatever gas, including hydrogen for sure. And then the liquid hydrogen, it is also possible from 25 to 45% of the stored energy is required to store the hydrogen. And however, this method is very high density of the energy, which is used. We need to apply the cryogenic condition about minus 253. And then in the metal hydride, yeah, I think this is for the storage, for the solid storage. This is relatively many in industry also already starting now, starting maybe 5 years back. Many in industry already apply this one. But again, the main problem in here for me is for the such kind of this technique is a little bit difficult to develop this metal hydride. Even not only for a metal hydride, like metal alloy, also for me, I think it's difficult. There are too many volatile condition when it's poisoning with the air, it becomes the oxide, or maybe some explosion also will happen or whatever. Therefore, for us, we are focusing on the carbonaceous gas because the carbon is more, I think, more inert and also fast available over the world, and we can create um, or engineer the surface area or the structure as good as possible. For sure, for currently, if we compare with the metal hydride, is still um, far. Some of the research almost similar with the performance of the metal hydride base. Okay, so this is our scheme of our research. Actually, this research is still ongoing. We are just finishing our first year of this research. So we try to develop the carbon gas, which is based on the graphene oxide or carbon nanofiber, the the CNF that we have, and or CNT. I will showing to you some of our progress, maybe not all the result because we still not yet filling into the patent and also into the journal. I'm sorry. I'm sorry, before I going further, this is just to remind you, this is the DOE requirement of the ideal condition of the storing of the hydrogen in the solid state, like the low operating pressure, if possible, about 3 to 12 bar, if possible. But there are many paper also I will showing you later in the next slides about very low vacuum or very high pressure about until 100 if I'm not wrong. And then the range of the temperature, if possible, about minus 40 to 100, about 100 degrees C. Because at this range of temperature is very common in industry. So this is what the OE targeted. Why? So that's the reason. And also the fast kinetic, this is regarding absorption desorption. If possible, about 1 to 2% of mass per minute or 2.5 minutes. Okay. So this is the timeline of our research until, but maybe into the system we not possible for currently, just maybe until the storage, I think. Okay, we just want to highlight again what kind of the storage of the hydrogen is possible, the most possible. On the top part, in the upper part, this is the physical bag. This is very already established, like compressed gas, cold compressed and liquid hydrogen that I already mentioned before. And on the bottom part, like the material base, which is our concern, is still many possibilities for research to advancing to make it more efficient or whatever in order to make it more visible, like the physical base one. For the material base, there are two types, chemical sorption and physical sorption. We are focusing in here for sure for physical sorption one, which is focusing on the carbon materials. Actually, for physical sorption itself, there are many, not only carbon, like zeolite. Of course, in here in Indonesia, we have zeolite, mineral of zeolite, many. Carbon for sure, we also can directly like graphite mineral or even from the biomass. Metal organic framework, there are so many advancing in the recent journal, many using this more both for supercapacitor, for battery, or many other applications actually, and many others technique also that we can use for the storing of the hydrogen. Okay, if we want to clustering like the material base and physical base, the physical base that I mentioned before, usually 250 or 700 bar for compress. The liquid one using about minus 253. For the PC option, we can use MOF, COF, CNT, zeolite, graphene, and etc. And this is the condition of the current of the conditioning in experimental. But minus 196 or about almost minus 200, little bit lower than the cryogenic one. So we can still far to bring in the room temperature if we want to get many sorbent in the volumetric condition. And then the pressure is usually up to 100 bar. Therefore, the DOE requirement, if possible, is less than 20, less than 30 maybe, if possible. Okay, but however, 100 bar is not so high comparing with this one, 350 and 700 bar. There are still many compressor even in our country, Indonesia, that can operate at this condition for sure. And then this is for commercial option like metal hydride, like, lanthanum pentanickel, lithium borohydride, aluminum alanat, magnesium hydride, LOHS, and etc. So this is the conditioning, usually about 300 to 400, and the low gravimetric density less than 2 weight%. For the carbon itself, about 2 until 5% weight, if I'm not wrong. Okay, next slide. So this is similar actually, but yeah, there are so many clustering of the storing of the hydrogen actually. We are focusing on the red one here, and you can see that there are many like carbon nanofiber or carbon nanotube, graphene, clatrate, and so many others. Even like fullerene also, because fullerene also similar with the carbon one. Zeolite, metal aluminum, etc. Okay. Yeah, this is the conditioning of each the storage technology, like in the liquid. So the operating temperature, like this is minus 253 again, and this is the comparing corresponding energy to release hydrogen in megajoule per kilogram hydrogen. You can see here, and then the compressed one, and also the alanat, metal hydride. So it is the water itself, of course, just for comparing. If you want directly from the water, you need about more than 1000 degrees C. Okay, so for sure this is not feasible for in the industry. Okay, for the storing of the black material base, as mentioned before, and this is the reported storage capacity. For the chemical, yeah, there are the weight of the hydrogen that can store is higher comparing with the physical one, like the ammonia boron or even the ammonia consider high the hydrogen that can store, and metal hydride, also alanat, formic acid, yeah, some format, carbohydrate, and LOHC for 7.2. For the physical itself, the highest is the microsphere glass and capillary glass. But yeah, this is rather difficult. Most researchers doing advancement on the carbon base and zeolite base, because those two resource is fast abundant in our even in our. But the highest in here like about 8 and 9 point. Okay. And okay, this is the metallic base. For the hydride base, they are. I just want to highlight the metallic condition of the metal hydride base so far. So the weight percent of the gravimetric, like the magnesium borohydride here, the highest one. For the volumetric and the gravimetric comparing with other. And this is sorry, this is the targeted of the DOE, for the solid storage hydrogen. So the H is meaning the hydrogen, and the M is the metallic. So they can interstition into the pore of the metallic ether. So this is the condition of the absorb, but this one the dissolve. So this is another example of the. This is focusing for the lanthanum pentanickel for the chemical process, chemical sorption. So this is like the VET process, absorption desorption, and then this is the kinetic absorption desorption testing. Yeah, this is the properties of the lanthanum pentanickel itself. Like this one, they have the density about 8,400 kilogram per meter cubic, and then this is the permeability number and the enthalpy, reaction, and porosity about 0. Okay. So when we have the sorbent material, then we have to put it in the storage tank itself, right? So this is just the schematic view how the hydrogen is stored in the vessel. And actually, if you interesting, focusing on the how the hydrogen is stored in the solid storage, this is also still can be more optimized. For instance, you can using RSM, responsive phase methodology, or another DOE in order to simulate this one. Yeah. So like how much the maximum of the sorbent, the solid storage, solid state sorbent that we must put, what the maximum volumetric that we can put in here, and etc. So this parameter we can more optimize with even with simulation, and then later on we doing the experimental for sure. So this is the conditioning when we want to do in the experimental condition after we optimize in the simulation. And if the storage tank itself, there are many ways. The container itself, yeah. Okay. So this is the conditioning the metal hydride in the experimental condition in the facilities lab in here in SAIAMC, the facility. So how much that laboratory that we need to prepare for the metallic. Actually, this is also similar like solid storage one. The conditioning in here, like they're using the 30 to 80 bar, high pressure until up to 200 bar, and then the lower pressure is less than 220 bar, and there are so many other also facilities that we need to consider. Okay, so this is the integrated system like this one. The information is from here. The report like what kind of the compressor, the consumer, that many others like the gas cylinder and etc. Maybe I will not go details here. Okay, so this is the concept of the PC option itself. Like this is the adsorbent. For instance, we have the graphene or graphene oxide, or even the CNT or active carbon, yeah, a carbon active, and also the absorptive element itself is like hydrogen, or maybe if we want to talk about the CO2, it also can depend on what we are focusing on. Okay, so this condition is possible for the reversible absorption desorption because this is only very weak force only on the surface, not like bonding like in the chemical state. So this is just the schematic how the graphene or the carbonaceous base like carbon nanofiber for the as the storing media of the hydrogen when it put in the tank also. And yeah, there are so many options for the carbon base like using activated. Even there are also some options like activated charcoal in here, but I'm not sure. I'm not yet further detail elaborate about this research on the charcoal. The one that I already studied is about using the CA, activated carbon, CNT or nanotube. There are also many. Okay. Meanwhile, for the hybrid, there are many alloy, intermetallic, non-crystalline complex, and many others also. Okay. So if you are curious about the morphology and of the morphology of the carbon itself, on the top part is the CNT, carbon nanotube. The lower part is the graphene from the graphene. So, so this is the condition of the storing of the hydrogen in the solid state condition. Like the hydrogen molecule are attracted to the carbon material on the material surface through van der Waals interaction. So this is very weak force leading to adsorption. And then the desorption, on the other hand, likely occur when the conditions such as temperature or pressure are changed. Meaning like we increase the temperature or increase the pressure, and then it will release, causing the hydrogen molecule to detach from the carbon material surface. So this is the basic condition, adsorption, desorption in the carbon surface. Yeah. And then the adsorption and desorption of hydrogen in carbon material can be influenced. Therefore, this is our focus of research. Can be influenced by factors such as surface area, pore structure, and surface chemistry itself. Meaning, we still can also load it with some catalysts like nickel, PT, or many other, but only put in small percentage. And this factor affect the interaction between hydrogen molecule and the carbon material surface, and ultimately impacting the adsorption desorption capacity. Okay, so this is the basic condition when you are interested doing the hydrogen storage based on carbon material. Okay, this is our data, but actually we cannot showing, but yeah, just slightly. Here, we comparing with graphene, multi-wall carbon nanotube, activated carbon, and activated carbon with treated. And you can see here, even comparing with the graphene, the activated carbon is superior in terms of the hydrogen absorption capacity. Please remind, this is just chemisorption testing the H2 TPR that we are already testing here. But this is not represent all the material as the solvent material. Therefore, we need another testing, the one that Dr. Xiong already showing. But unfortunately, in our institute, we still not have that facilities. Maybe later I will asking to you, Dr. Xiong. Okay, so this is our hypothesis. We have the two hypotheses in here. So nanopore enhance the hydrogen absorption capacity. In the hypothesis number 2, the acid treatment to increase the active surface is expected to increase the absorption capacity of MWCNTs. And open cap and surface functionalization of MUWCNTs is to increase absorption capacity. I think this is just the carbon one, right? So we need to enhance the surface area or the pore size, the pore distribution, I mean, the pore distribution with the certain pore size diameter. Okay, this is also another our result regarding with the we enhance with the ultrasonication. Maybe I just skip it. And yeah, this is I took this is from another research actually. This, they using the biomass base. The biomass base as the maybe we can call it as the carbonization activation, yeah, carbon active, activated carbon, I think. So they are successfully using this catalyst in OH and N2SO3 in order to deteriorate the cellulose, some cellulose and lignin also in their surface. So the some pore with the high, I think this is very high surface area, about more than 2,000, even more than 1,500 also I think is very high surface area. So they successfully achieve almost 3,000 meter square per gram. This is very high. Therefore, the hydrogen capacity of their research is very successful. Okay, we can see from this table, we can see that the okay, this is the pore size that they achieve from all of the sample type they have. This is the surface area BET base that they obtain. Almost all of this material higher than 2,400. Okay, and then about the hydrogen performance of storing, like this one. So the on the left side is the relative low pressure, relatively vacuum, and then the hydrogen uptake they can achieve until 3%. And meanwhile, on the right side, we can see this is on the absolute pressure. They put the pressure until 50 bar. Meanwhile, in the previously, I showing to you, there also they put until 100 or 200 bar. Of course, this depend on our purpose. If possible, as I mentioned before, less than 30 bar, if possible, right? So the economic or the feasibility when we want to put it in the mass scale will be feasible. And again, you can see there from the y-axis, the hydrogen uptake is low. Yes, and this is the challenge. Comparing with this one, yeah, in the vacuum or in the cryogenic, it's easier to absorb, easier to storing. But in the room temperature or like in the, even though we put some pressure in here, the hydrogen uptake is not so far comparing with in the low vacuum. Okay, you can see here this the B. This one is at the condition 298 Kelvin, about how much Pak? About 27 degrees C, yeah, about. And yeah, the pressure is up to 50 bar. Meanwhile, in the left side is 77 Kelvin. This is the liquid nitrogen state, meaning about minus 200 degrees C, right? I think about. And this is condition 1 bar. So for sure, the temperature and also the pressure will affect into the performance quality of the storing of hydrogen into materials. Yeah, this is the result of their work. So yeah, hydrogen uptake is about 3. This one, right? About 3%. There are also many other biomass. They're using sawdust also. Bamboo. Sorry, this is comparing with other research with similar using biomass. Yeah, I forget to mention to you. Our research also using the biomass base, which is from kelapa sawit. Huh? Kelapa sawit and bagas. Bagas and also sorry, with coconut coir and bagas. Sorry, I just remember. So this is another other research. They are also using the biomass waste like sawdust, bamboo, cellulose, corn cob, chitosan, fungi, neol market, chitosan, beers, and many others. Yeah, there are many ways in the research aspect that many researchers also want make some breakthrough in order to the storing of the hydrogen make it feasible in the reality. Okay, again, this is just to give some perspective to what kind of the carbon-based solid hydrogen storage that we can use, like CNT, graphene-based, carbon nanofiber, nanopores carbon, carbon aerogel, fullerene, and many others. So many, okay, and then so this is the interaction, like the weak interaction, like using the on the walls, right? As I mentioned before, and if possible, you also can put some catalyst, but only a few. And maybe if we using some catalyst, it will enhance more. I will showing to you some that using catalyst and without catalyst. Okay, so this is only the surface interaction of the hydrogen and the carbon. Yeah, this is the carbon-based material that we can use for the turbine of the hydrogen storage. Okay, this is to highlight it again, what the targeting of the DOE goal for the hydrogen storage, the gravimetric capacity, like the material base, it will be like the achievement of the target of the 2025 about 1.8 kilowatt hour per kg for the material base, right? And this is the ultimate target. So the number like this one and the volumetric capacity. For the volumetric capacity, if possible, about 1.7. But this is unit in kilowatt hour per liter. Before is mole per gram or any other different unit. Yeah, all of this the ultimate target from the Department of Energy in order for the storage goal hydrogen solid based on the solid state. Okay, maybe if you also curious what kind of the morphology of the carbon as the solvent material. So this is the multi-wall carbon nanotube, graphene oxide, and also GO and RGO combined with the multi-wall carbon nanotube. So the performance is quite different. Again, this also have the hydrogen uptake or absorption about 3, but this one is less than 3 comparing with the previous research, right? Again, so this is such kind of the morphology that we need to achieve. So the pore size is usually about the less than 100 nano, 20, 30. Maybe I will show you to you later on. Okay, this is another performance of okay, this is from the activated carbon, right? The activated carbon derived from a mini biomass bioresource. So this is the different temperature for the hydrogen absorption capacity. This is the one that I told you before. They also using the nickel, nickel as the catalyst for the HCS, the hierarchical carbon scaffold, in order to increase this one, the D, the D figure, in order to increase the capacity or the uptake of the hydrogen. Indeed, they have some such a difference comparing with without a nickel. This one, and yeah, this is a condition for the A, the figure A on the top left. This is the condition, the experimental condition that so far, yeah. like price hash at what temperature, what pressure, coffee bean, jute fibers, corn cob, and many other also. So maybe this we can use as our reference if you are concerned, if you are interested to doing some research on the hydrogen storage. Okay, this is some experimental result. So we have two, experimental and theoretical. At the first, I want to show you the experimental result of many biomass base for the carbon base, yeah, sorry, especially the carbon base as the hydrogen storage or storage sorbent material. This is AC, activated carbon, with the doping of PT, and you can see TNT, multi-wall carbon nanotube, carbon nitride, porous graphite, and many others. So this is the conditioning of temperature, pressure, hydrogen apex. The hydrogen apex so far, I think about from this about 5, huh? It is, but this is alloy, yeah, for sure. Yeah, GO, sorry, AC, yeah, with the palladium, activated carbon with the palladium, they can achieve about 5.5 from, yeah, is quite high. And then, yeah, because we know palladium also a little bit poisoning maybe, but that's as a catalyst very good. And multi-wall carbon nanotube with combining with GO, graphene oxide, RGO alone about 1 point still low, and yeah, many other also you can consider in here from here. So the next one is from the theoretical. So this is from theoretical. Yeah, we expected a higher than 5 if possible, right? Here like aluminum absorbed graphene. So this is the combination of Al with graphene. So it can achieve about 13.79 or almost 14%. Is considered very high, right? So yeah. Okay, I just highlighted again. So this is the carbon fiber. So if you want to know like the what kind of the morphology, so the ABC is no any treatment. The DEF they have some treatment, and GHI is another further treatment. So the pore size, the pore distribution is different between the second line and the third line in here, and also the pore size that developed between the original, the virgin one, and the last line in here. So for sure, the last line is the ideal one as the sorbent material of the hydrogen. And indeed, this is also not easy to achieve like this. Okay, I continue. So this is their condition. This work until APCF and etc. Here, this is their work, and yeah, comparing with other, also they are very superior, about 5 point something for the hydrogen uptake or hydrogen storage condition. So again, this is still condition in the cryogenic in the 77 Kelvin and 10 MPa, the pressure about 100 bar with the PD loading deposition in here with the code of the APCFH 0.3. So they further make some optimization in here. So the storing capacity is about 5 point something, all of them. And yeah, on the low part, you can see that the SEM, TEM, ADS mapping, SIA8, ADS spectrum, and also the diameter distribution. I think this is PSA, yeah, the PSA analysis. So from the SEM also, it's clear. The pore diameter, the morphology also is very beautiful for this kind of the sample with the name PD 0.5, APCFH 0.3. And the pore, the particle size about 41.7 nano, about, yeah, the average diameter. So the range is from 10 to 80 nano they have. Okay, this is not pure carbon, but again, we also have this one, especially from the PLN. Fly ash, so the fly ash itself, actually we can we can more provide is like in zeolite-like material. Zeolite itself is very good as the absorbent from long time ago for any other application, including for the hydrogen storage. But again, in here, the zeolite itself, we can template it with the carbon in order to enhance the hydrogen uptake capacity or hydrogen efficiency. This is just general step. If you want to utilize the fly ash as the resource of the zeolite, then after that, the zeolite is templated into carbon as the sorbent of the hydrogen. Okay, so this is the illustration, the schematic illustration, the zeolite Y, and then the zeolite and carbon composite, and this is when it templated, we call it ZTC, zeolite templated carbon. So this material, the C figure, is have a huge performance, high performance comparing with the pure of the zeolite. Okay. So this is the condition of the hydrogen uptake. Yeah, again, if comparing with the previous, like from the carbon and the chip, still lower. But again, we have the valuable of the fly ash in the power plant industry or any from many other activities also. Then if we utilize to like this application, I think it's very good. So this is the loading condition, like 78 Kelvin. Again, this is like the nitrogen liquid condition in 1 bar. But this one is in the room temperature and 1.38 bar condition. Yeah, the hydrogen uptake or the hydrogen storage capacity about 1.6. Yeah, and oh, this is the micropore. Okay, so this is there are some conditioning of this condition of the material ZTC, zeolite templated carbon, and yeah, the commercial one. This is the commercial one, zeolite X and zeolite templated carbon. From this one, they further treated. So the hydrogen uptake is increasing. Yeah, about almost 30.5. Meanwhile, for this is in the low pressure. This is I think sorry, similar pressure from 0 to 1,000 millibar or 1 bar, okay, meaning this is in the low pressure until into the CP condition, I think. Yeah, but when the zeolite templated carbon itself is more modified, it has the capacity uptake is higher than even with the commercial. Okay, so this is just to highlight it. There are many advantages of the solid storage of the all material, yeah, for the hydrogen storage, like the metal organic framework in here, covalent organic framework, porous organic polymer, carbon-based material that we talk about, and also the zeolite. The most favorite one for me is the left two side here, carbon-based and zeolite-based. So you can see here there are some advantage, like for instance for carbon, high thermal and chemical stability, ease of processability, inexpensive because fast abundant, yeah. But the disadvantage, like of binding site for hydrogen, therefore we need to modify the surface area or put some catalyst loading, even though a little. Non-uniform pore size. Sometimes it is difficult to make the uniform of the pore size. Hard to control the pore structure. And again, this is for the zeolite, for instance, high crystallinity. Yes, of course, the zeolite is the crystalline material, thermal and hydrolytic stability, and inexpensive also. Yeah, in Indonesia, we also have zeolite or mineral-based zeolite. Lack of binding site, similar with the carbon, limited structural diversity, low gravimetric hydrogen uptake, and tunability. And of course, this all these conditions that we need to overcome, and therefore we need the research. And okay, this is maybe this is the expertise of Dr. Xiong, I think. Maybe there are some apparatus that you already mentioned as similar with this function of the CPOC apparatus. Yeah, honestly, we not yet have this apparatus. We plan to study of the hydrogen storage using this one. And yeah, maybe at the first we want to develop like the prototype, but micromagnetic, if you have like this one, I'm very interested. Maybe the Tersiong after, maybe you can explain further. So actually, the conditioning of the concept basic is like this one, the transport of the thermodynamic that can the low pressure or low temperature conditioning. The blue one is the nitrogen, liquid nitrogen, I think. The conditioning like low temperature. The one that many research also showing like 77 Kelvin, 78 Kelvin, similar lah. And also like this one when the dissolved condition. Like that. So this is only the concept of the acceptance disruption based on the Sievert analysis. Okay, I think for the carbon base it's finished. So this is just the storage or the transportation of the hydrogen just globally, like from transport, storage, hydrogen refilling station, refilling option, what kind of this is the schematic in the real condition. Or for sure, the storage not yet including in this system, in this supply chain. Okay, I just want to highlight again, this is some application that for the hydrogen already in our real life, right? For train, for aviation, it will be 2035. For the car already, like the hydrogen BMW, Jaguar, and many others, like Toyota Mirai, Honda Clarity, and many others. So this is just to showing to you that how fast the hydrogen, but this is the gas pressure best condition, yeah. This is for mobile, like for the this one. This is like from Linde, and yeah, like this is from Tucson, Mirai, Clarity, Nexo. There are many brands also that developing the FCV, fuel cell vehicle. Okay, from the right side here, actually this is for the charging station of electric vehicle, but this is powered by fuel cell. The top one is from SOFC. The bottom one is alkaline base, alkaline fuel cell. Okay, this is the conditioning of the pressurized physical base. Okay, I just keep it. Okay, and this is the LCOH, the LCOH of the hydrogen. Like this is from the natural gas. Yeah, and at the 2050 it will increase more the price due to the decreasing of the green or green hydrogen or renewable hydrogen, and the natural gas. This is sorry, this is without TCS. If this is with TCS, carbon capture storage, and the coal will be increased more pricey, yeah, at the 2050 if expected, and then this is the coal with CCS maybe still can compete with this one. Okay, this is just to showing you that the future prospect of the hydrogen in the real application in industry. Okay, this is for the pressurized or the storing of the hydrogen both in the cryogenic, in the liquid, in the compressed gas. Just the basic phase diagram. Yeah, there are many like compressed gas, cryo, and subcooled liquid called cryo. And this is just the storage tank, not the sorbent media. The storage tank, like for the compressed, the cryo, and liquid, the condition or physical condition that required. And this is for the liquid hydrogen tank. Yeah, even for the aerospace, like in here, like JAXA also, they're using this one for the aerospace, liquid base, liquid hydrogen. And for the aviation, that I mentioned before, this is also actually using the liquid base. Okay. Called cryo compress. This is especially for the BMW. They're using the cryo compress condition. And okay, if we talk about the compressed gas, the tank itself, they are already evolutionized. Yeah, maybe. Currently, it's type 4 that comprising of fiberglass, carbon, full wrap with plastic liner. Therefore, this is suitable or the most suitable for the hydrogen. And there are some conditioning in here, like the pressure, diameter, length, and etc. Those two, like I mentioned before, the conditioning of the compress like 350 and 700 bar. Meanwhile, the liquid, the density is in here is very high. For the compressing, only about this condition. Okay. Yeah, this is the some the mark from the industries that available of this type of the tank. Okay, I just skip this one. Okay, this is the latest of the storage tank is on the carbon fiber, or the type 4 thing. Yeah, like this one. So this is the anatomy of the tank itself for the hydrogen, specific purpose for the hydrogen storage. This one also, this is from Dusan. Just highlight it. Okay, and this is my remark. So there are many storing of hydrogen, for instance, like compress. It can be used to store small quantity of gas. And storage hydrogen in liquid can be used for storing large quantity of gas for longer time, however, at high energy penalties for liquefaction. And for the porous media that we're talking about, it may offer an advantage for storing small quantity of gas in medium to long term. Maybe that's all from me. Thank you. Back to you, Pauka.
Q&A session. Okay. I think we already have a question from the Zoom audience. Let's go from there. Okay. Oh, this is question for Dr. Wen Xiong. Dr. Wen
Okay.
Xiong?
You want me to go
Alright.
through one by one?
Yes, so this questions from Anang Adyagaha. So he has a 5 question for you. Carbon neutral, net zero, zero emissions. What are the difference? What is the purpose of gas absorption? What is the mechanism of gas absorption? What is the instrument for gas absorptions? Is absorption of gases on solid reversible, irreversible? I think they are all related, so you can please go ahead and answer.
Okay. So for the first two questions, the carbon neutralizer and the net zero and zero emission. If you really want to see the difference between those terms, you can go to Google it. It's going to give a better definition than I told. So I'm going to talk about the difference briefly. So the CO2, like the carbon neutralizer, we are focusing on the CO2. So we say we produce how much CO2, we have to deal with how much CO2. That means we are not going to emit any more CO2 to the air. So for the net zero, is talking about the actually net zero technology. So that means, like I mentioned in my presentation, mostly when we talk about the net zero, we are talking about the CO2 net neutral and the clean hydrogen, clean energy hydrogen. Like also we can involve others, but those two are the very most representative net zero technology. For the zero emission, I guess it has a wider range than the CO2 nature. So for the zero emission, you have to consider other greenhouse gas like the methane or SO2 or others. So if you are really interested about those one, you can Google and then find the exact definition for those. Okay, for the second question, the gas adsorption purpose is trying to using different kinds of gas molecule as a probe to detect the surface, the solid surface, how the surface look like we say the surface pore size, the pore structure, the surface area, just want to see how the surface look like. We are not able to see it by our eyes, so we have to use a tool, which is a gas molecule here, as a tool to detect how the surface look like. We want to see kind of like using the gas molecule to image the surface, the solid surface. And then the third question, the mechanism of the gas adsorption. So I mentioned in my talk, for the gas adsorption, we normally talking about the phase absorption and the chem absorption. So the mechanism of gas adsorption is through different kinds of interaction from the gas molecule to the surface, either by the van der Waals, the weak induction, or by the chemical electron sharing or transfer, which is the chemical bond. So that's the mechanism of the gas adsorption on the surface. The fourth question is talking about the instruments for the gas adsorption. We normally divide the instrument based on the gas adsorption types, as I mentioned in the third question, phase absorption and chem absorption. So we normally talking about the instrument, which is the physical adsorption analyzer or the chemical analyzer. Our micromeritics are focused on the static voltammetric method of the phase absorption analyzer. And then for some other suppliers, they may have the graduative adsorption method, but we don't have for the micromeritics. And then for the chem absorption, as I mentioned earlier, our most widely used system is AutoChem 2920, and then now we have been updating to 2930. For the fifth question, the adsorption on the surface is irreversible. The answer is yes or no. When I say yes, it's talking about the chem absorption. Like I mentioned earlier, the difference between chem absorption and the phase absorption is chem absorption is selectively on the support, on the surface. So if we do not do anything about the desorption, the surface is irreversible adsorption at the same condition, which means at the same temperature. But for the phase absorption, it's normally reversible even at the same temperature. For example, the 77 K. So the equilibrium is kind of like a dynamic equilibrium. So it's reversible adsorption or for phase absorption. Any more question beyond that?
Yes, I hope that satisfies Nana idea of Graha. Do we have another questions? Slide number 2. Okay. Oh, from Nanang Adya Graha. Seems we still have more question for you, Dr. Wen Xiong.
Okay, I will go through one more. Okay, the first one,
Yeah.
he's trying to ask what are the factors affecting the adsorption of gas? I guess the second one is going to ask the same question. What are the factor affecting the adsorptive? So it depends on the adsorption type. Like I mentioned, for the phase absorption, if we are talking about using the static measurement, during the adsorption, we normally care about the temperature. That's a very, very big problem that we have to control during the testing. So the temperature, the gas, like species, different kinds of gas, and also the pressure. So different pressure, different temperature, different gas will affect on the surface with different behavior. That's phase absorption. And then for chem absorption, absolutely the temperature, the gas will be the same. But for the chem absorption, we're normally talking about at one atmosphere adsorption. So the pressure doesn't change during the chem absorption. But it's changed, it's going to be different. So that's the two difference between phase absorption and chem absorption. If we are looking at the gas law, ideal gas law, or even the gas state, gas equation of the state, we have to pay attention to the difference between gas species, temperature, and the pressure. Those are the three different kinds of things we have to pay attention when we're talking about the gas adsorption with different kinds of surfaces. The third question is, what are the requirements of adsorbent? It depends. So let's also talking about the phase option first. So for the phase option, typically people are using nitrogen as the, he's talking about adsorbent. You have to, you have to specification the application. So for example, if you want to separate CO2 from nitrogen, then your adsorbent has the ability either highly selective adsorb the CO2 or highly adsorb the nitrogen, trying to separate those two. That's for the gas adsorption. And then for some gas storage case, your materials, your adsorbent has to have high storage capability of specific gas, like the hydrogen storage, we have been talking about a lot today, and CO2 storage, and different kinds of storage. And then other case is trying to remove the impurity from like a gas mixture. Then the same idea here, your adsorbent has to have the ability either highly adsorb the impurity or highly adsorb the other component in the gas mixture. For the first question, what is the mechanism of membrane adsorption? So most of the membrane actually are made by different kinds of adsorbent. So the people or research kind of like using the adsorbent to make membrane is for some specific application. So they don't want to use the powder adsorbent as a application materials. So they kind of like using the adsorbent to make the membrane. The mechanism is going to be the same as the adsorbent, like the gas should go through the membrane or should not go through the membrane for the separation. This another advantage of the membrane is if you use the adsorbents like membrane, like multi-layers, you kind of like can adjust the structure of the membrane to selectively separate different kinds of gas. For the fifth question, what are the advantages of adsorbent membranes? Like I just mentioned in the first question, for some specific or for some industry application, people cannot use the powder adsorbent or even some formed adsorbent as like their industrial conditions. So they have to build using the adsorbent to build some adsorptive membrane for their real application. So the advantages is like they can be used for longer time. Like for example, they can use for like years. That's one advantage. The second one is very easy to operate for the some operator in the production line. So if you are deal with the powder adsorbents, most of them are like a researcher. But if you want to go to the production line, people like some operators, they don't have the ability to do that. So that's why for convenience or for some specific application, people want to build some adsorptive membranes.
All right. Thank you, Dr. Wen Xiong. So let's move to the slide number 3. Question for Dr. Denny from Primalia NG. Number 1, which method holds the most potential to store hydrogen in future in terms of hydrogen capacity? And question number 2, which one holds the most potential between chemisorption and adsorption method to store hydrogen in the future? Mr. Denny, please.
Okay, thank you for the question. Is it audible? Okay, so thank you for Primaria for the question. Okay, so as I mentioned before, there are many methods, right, to storing. Again, I cannot decide it now. It depends on your longer, it depends on your capacity, right? There are also the distance. If you want to like among the countries or the over the seas, of course, which kind of the method it is suitable. We cannot just put one method for all. It's impossible. Yeah, and that's a not good decision for sure. Like, is it should be liquid or should be the chemical option or whatever? So it depends. So just for like a story, like in the stationary, it different with the mobile. Across the island and or across the country, it should be like in the liquid state. Even in liquid state also, if there are two types, for instance, in the pure hydrogen or non-pure hydrogen, meaning like the uh, carrier of hydrogen. For instance, using ammonia, using LOHC, liquid organic hydrogen carrier, or many other liquid state that can carry the hydrogen in the fast number or weight or volumetric, right? So number two, comparing chemisubstance, physicsubstance. Yeah, if our target only for the research, it depends on your facilities. Yeah, chemisubstance also good and physicsubstance also good. It depends on your, I mean, the facilities and also because both of them has advantage, disadvantage. If possible, the chemisubstance also you can do like the metallic base, the metal hydride or whatever. But as I mentioned before, there are also some problem that we need to overcome, and it's not easy to make the alloy, right? Therefore, we are more focusing on the carbonaceous base or like zeolite. It's easily to treat. I mean, but again, this is only for small capacity or only for like station capacity or only for the short range uh, hydrogen transportation, for instance. Yeah, it depends on the condition or situation. I hope it answer your question.
Thank you, Dr. Denny. To the slide number 4. Which one? Oh, okay.
Any is okay.
Okay, this is for Dr. Denny from Nanang Adya Graha. I think that's quite clear. Please go ahead.
Yeah, I already mentioned here in my introduction. There's the challenge for sure. The hydrogen due to that very low volumetric. Yeah, but the gravimetric is high, but the volumetric is because we know that the density of hydrogen is very low, yeah, very light. Yeah, and therefore, how to store, how to compress, or to liquefy it requires some energy also. Okay, the rule you mean the standard, the standard or like the DOE target, that is the standard one, how the capacity that we need to overcome, that we need to achieve. Yeah, you can focusing on that one. The table I'm not remember all. There are so many parameters that we need to pay attention on it. And why is hydrogen more difficult? It again because it's very light element in the predictable is on the top left, right? Yeah, I hope that answer your question.
Thank you. Let's go to the next one. From Andi Nafis Annafi, University of Brawijaya, for Dr. Wen Xiong. Dr. Wen Xiong,
Yeah.
number 1, how do you determine the physicsubstance and chemisubstance process between the absorbent and the absorbent?
Okay, yeah. Okay, so generally, when we say physicsubstance, we are talking about the gas adsorbed at low temperature, like for example, the liquid nitrogen temperature 77 K. And then for the chemisubstance process, we normally talking about the high temperature, which is like long temperature, all the way to 200 degrees. So we can see the feed absorption or chem absorption separate testing in different temperature. That's how we normally generally do the determination of the feed absorption and chem absorption. If you do have the feed absorption or chem absorption at one sample, you really want to see the difference, you can do some control experiments, like for example, using our 3-flex, you can throw the CO2 or hydrogen, which is mentioned here, to the sample, and then see the gas adsorbed, how much gas adsorbed has been adsorbed on the sample at some one certain temperature, let's say 20 degrees C or 0 degrees C. Then you see you have the total amount of both feed absorption and chem absorption amounts, and then you do the evacuation for some enough time, like 2 hours, 3 hours, whatever you need. And then during the evacuation, the reversible feed absorption will desorb from the surface. And then you do the throw CO2 or hydrogen again to the surface. At this time, the second time, the amount of the gas has been adsorbed on the surface is the feed absorption amount. So you did 2 experiments here. The first one, you get the amount of feed absorption and chem absorption. The second time, you get the amount of feed absorption. So here you can distinguish the amount between feed absorption and chem absorption. That's one way to do that. The other way is using the temperature program desorption. You throw the CO2 or hydrogen, like for example, the AutoChem in a flow system to the sample, and then the sample will both feed absorption or chem absorption the gas on the surface. When you throw it for like certain time to saturate the surface, like 3 hours or 6 hours, whatever you need. And then you throw natural gas, like the helium or argon, whatever you need, to the system, to the sample, and then do the temperature program from whatever you start, like 0 degrees C or even 25 degrees C. And then in this way, you are going to be able to see the gas desorption from the surface as a function of the time. So we normally, generally, we divide the feed absorption and chem absorption desorption temperature with 100. So if we say some CO2 or hydrogen desorbed from the surface at a temperature lower, like for example, from 0 degrees C to 50 degrees C, this part, the amount of the gas, we would say that's feed absorption. Or some CO2 or hydrogen dissolved at high temperature, like 100 degrees C to 150 degrees C. Then we say, okay, those gas has been chem absorption on the surface. So that's 2 ways how you can determine the feed absorption and the chem absorption.
Thank you, Dr. Wen Xiong. Question for Dr. Denning. Let me summarize it for everyone. He asked about how to address the heat that occur during the suction process. Dr. Denning, please.
To answer this one, I need to share my PPT again. Can I?
Yes.
Thank you. Yeah. Can you see my PPT? Okay. So I think this is the reason why for the adsorption process usually in the liquid or in the cooled condition, in order to make the hydrogen is more easy to adsorb. Therefore, they are offered by the liquid nitrogen. So this is only the illustration, yeah, for sure. But in the reality, you can make many other approaching. For instance, using the spiral one, using the liquid nitrogen or any other cooling system that make it more easier hydrogen to adsorb, right? So yeah, indeed, this is like the thermodynamic engine and many way that we can solve that we call it as the HMS, right? Heat management system. Yeah, correct. And we need to concern about that one. Otherwise, it also will dangerous. Okay, good question. Thank you. I hope you can help.
Thank you, Dr. Denny. I think we still have a bit of time, right? Okay, moving on to the next question. Now from Nanang Atyagraha again for Dr. Denny. What is the best material to store hydrogen? Number two, is hydrogen storage renewable? I don't know what that means. How long can hydrogen store energy? And number four, is hydrogen storage efficient? How efficient is hydrogen power storage? Dr. Denny, please.
Thank you, Nana, for asking again. Wow, you so actively asking, yeah. Again, some of them I already answered actually. The best material, we cannot decide it because it depends on the storing capacity in what condition that you want, right? Yeah, but if you talk about only for research, as my suggestion, my recommendation, this carbonaceous base or zeolite base is enough for me. You just make it a more some advancement, some modification on it. I think it's good, right? But again, if you want to like in the high capacity or in the high scale, in the big scale, for sure we need to do some more evaluation and FS feasibility study further, right? So in term for that one, still long term, still later. So is hydrogen storage renewable? The material, you mean like the using the biomass base, like that one? So it's sustainable, maybe not renewable. I mean, oh yeah, maybe it's also renewable. You mean like in terms of the capacity, the usability of the material? Yeah, it's similar like for the physics option, yes, for the physics option, but of course there are also some limitation. Maybe the structure will change, right? Because there are some the temperature change in the pressure change also. Yeah, for sure. So which one the best? Of course, the crystalline one is the best, like the zeolite zeolite one. So, but there are also some research that I already did showing to you that the mixing of the zeolite and also the carbon, we cannot rely only on one type of the material. So we need to combine it so it will can good optimization. So my suggestion, if you want to do that one, like for simulation first, you can do, right? Many some simulation for doing that one before you going to the experimental one. And how long can hydrogen store energy? Yeah, you mean when it compress, how long it will stay? Maybe there are some leaking. It depends on the quality of the storage state, okay, or the adsorbent material, how it can absorb. Like the chemisorption for sure is much better than absorption, right? Therefore, if we want to long term, mid term, and very short term, we need to decide which one is the best for what kind of application. Is hydrogen storage efficient or efficient is hydrogen power storage? The highest one for the hydrogen uptake capacity is about 10 plus, only about 10. Most is less than 10, 8%. I think that's therefore we need to increase more the capacity, the reactivity, whatever. But if you talk about the chemisorption, much better or the liquid one.
Thank you, Dr. Denny. Let's moving on to the next one. This is from Nano Swan from Redo. Before Dr. Denny. Number one, what are the prospects of using TIC technology, and are there recent studies and challenges on development of this type of material in terms of future defense technology sector? Number two, according your presentation about kind of material absorptions like absorption, chemisorption, and a few kind of material like zeolite, CNT, graphene, sorry, which one suitable for defense environment or for special method approach and material for use in this sector? All right, this is interesting. You can go ahead.
Hello, Mas Nano. How are you? This is
Halo Mas Denny.
Prof Jarod student. Long time no see ya, Mas Nano. Oh, very good question and tough question. Cannot answer exactly because it is very niche area application, right? So we need to perfectly study on which sector, on which application for the defense, even like for the hydrogen storage, for instance, like radio communication, that's okay, right? It's only we need to small capacity and the hydrogen we can connect it into fuel cell, and that's for radio communication at also can. Or even for like in the stationary for the again for the communication or for maybe in some remote, yeah, or just in the onshore, maybe they also produce the hydrogen or whatever. I don't know. There are so many. This is too niche area. I'm not sure, but yeah, maybe after this, Prof. Enya can add some information. Add small. Okay. Yeah, please. Okay. Prof. Enya, please.
Okay, thank you. Maybe I just want to add a little bit because we have a collaboration with SFC, our partner. They have several products of the direct methanol fuel cells that using on this telecommunication sector, as Dr. Denny mentioned. And they have several, not only the direct methanol fuel cell, but also that require methanol as a solution, but they have also the fuel cells from PEM, or proton exchange membrane fuel cells, with the capacity, I think, from 100 watt until 500 watts, yeah, and they have also 1 kilowatt and 1.5 kilowatts of fuel cells that use on the remote area, and then they apply also in the defense. So I think, but not yet in Indonesia. They have several examples in the Europe. The army that cross over the jungle, and they carrying the battery to use the communication to support the communication energy. They now replacing the battery with the hydrogen, and also they make some uses that replace diesel. They reduce the diesel also at the specific remote area, using by methanol, also by hydrogen. They use the quantity of transportation of diesel. They can reduce, I think, more than 50% uses of diesel that can be replaced by hydrogen. So you can check, I think, the website of SFC. SFC now is the partner. We have a collaboration with IFHE also to them. If you interest, we will ask them to send you more information that the hydrogen can be used in the defense technology sector. And I think the other one is for submarine application. But I think there is several examples that now is in the research activity, but not yet in the commercial. I think the submarine application also will be the future uses of the hydrogen. Thank you.
Thank you, Prof. Enya, for adding some information to this. I believe that marks the end of our discussion. Yep. I would like to extend my deepest appreciation to our esteemed speakers, Dr. Wen Xiong and Dr. Denny Sidky, for their insightful contribution, as well as to all the participants engaged this enriching sessions. Your question and insight have made this webinar truly relevant. In closing, let's remember that the pursuit of knowledge and collaboration knows no boundaries. Let's continue to explore, innovate, and work toward the brighter future together. Thank you all for being a part of today's e-talk webinar. Back to you, Mbak Wiku.
Okay, thank you, Pak Oka. As our appreciation, we would like to deliver certificate of appreciation to our speakers and moderator. Firstly, for Dr. Wen Xiong. Dr. Wen Xiong, could you please turn on your camera? And this is certificate for you. Thank you very much for your great presentation.
Thank you. Thank you so much for that.
Dr. Wen Xiong, could you please turn on your camera?
Yeah. Are you able to see me?
Okay. Okay. Next for Dr. Denny Sidki. Okay, thank you very much for your interesting topic and also discussion.
Thank you. Thank you for the committee.
Okay, last but not least for our moderator, Dr. Oka. Thank you for your guidance during our main session. This is the certificate of appreciation from IFE to Dr. Oka. Okay, well, as I mentioned before, committee has some prize for best participants with best question during the discussion. And the winner is first, Bapak Nanang from Adiagraha. Can you turn on your camera, Bapak Nanang? Okay, and the second winner is Bapak Nano Suwani from RIDU. And also Bapak Andi Nafis An-Nafi from Universitas Brawijaya. Okay, and committee will contact you from through chat column. So please don't leave the Zoom before we get your contact. We will send the gift to you. And congratulations, committee, have you already pictures? Yes. Okay, congratulations and thank you very much for your active participation. Well, this is the end of our webinar today, and we would like to ask Mr. Kurniawan as Operational Director of IFE to give closing statement. Please, Pak Kurniawan.
Thank you.
Yes. Okay. Alhamdulillah, the webinar will run smoothly. We thank to our speaker for today's webinar, Dr. Wen Xiong, for your excellent presentation. Thank you. And Dr. Denny Sidki, thank you for your comprehensive presentation also. And to Dr. Oka and the FIA team, guide and carry out this event. Tetap semangat. We thank to the sponsor, also ladies and gentlemen, all the participants who attend online until the end of today's event. We thank you. We have some information. Let me share first. Okay. Okay. Okay, the first one we have for the next webinar series. We will discuss also green energy and advanced material, particularly on particle technology. We held on next month on 20th of September. Secondly, our biannually event international conference on fuel cell and hydrogen technology. The history is first held on 2007 in Jakarta, and last one is 2019 in Bali. And the seventh conference will be held on 9 to 6 September in Putrajaya, Malaysia. For selected paper will be published in International Journal of Hydrogen Energy. For information, you can see the website. This event is collaboration between MAHE, BRIN, and also EFHA. Also, for those who haven't registered to become a EFI member, please register. We are open to all stakeholders. Please visit our website. You can see at the bottom. Okay. Finally, we hope this event can be useful for all of us and see you at the next webinar event. Assalamualaikum warahmatullahi wabarakatuh. Salam hidrogen. See you, Mbak Dewi.
Thank you very much, Pak Kurniawan. So this is the end of our webinar today. Thank you very much for all speakers, all participants, moderator, and also sponsor. Hope we can meet again in next event. See you.
Sabar. Bumper.